Hello everyone, welcome to the very first lecture of deductive verification. Here we will be continuing with the techniques that software verification has. And one of the technique that we are going to discuss right now is deductive verification, which is of prime importance while studying software verification. If you see, the entire series for deductive verification is divided into following parts. So you can see there's a part 1. This is the part 1 that we will be discussing. Here we will be talking about the introduction. So what exactly is deductive verification and how it affects the decisions while we are talking about the formal verification techniques. Secondly, we'll talk about Hoare triples. This is a very important concept which will then lead to Hoare calculus. The B part, that is the second part of our whole series, will have proof tabulux, and the third part will have verification conditions and weakest precondition. Later, we will be going into questions. Then we will talk about pharmacy from the exam point of view. The number of questions that can come in pharmacy, we'll do it in detail. And finally, we will be talking about tool. So if you are going through the series of deductive verification, I will urge you to go in this sequence so that you do not miss certain concepts that will be needed in the other parts of the video. Without wasting any time, I would like to start with deductive verification, and I would like to highlight the word deductive verification. According to me, whenever you are studying something new, you should pay attention towards the heading because the heading says it all. Headings are kept in a way so that you can easily deduce what it says. And when we talk about deductive verification, some sort of deduction needs to be done in order to verify some program. Now, why program? Because we are talking about software verification. And we are talking about software verification. That means we will be verifying what? We will be verifying software. And the general trend of writing a software is via programming languages. So I will constantly talk about programs when I'm talking about deductive verification. Now, your question can be, do we have something else as well? If not program, then what are we going to study? And my answer to that would be yes, we will either have a program or we will have a model. Right now, we are talking about the program. So, I will ask this question, is my program P correct? And if you don't understand why I'm asking this question, please go back to our first lecture. This will help you understand why we are asking this question. But all in all, we'll be asking this question, is my program P correct? And when I'm talking about my program P, I am genuinely looking into ways that I can make it correct. And what is the bad things that can happen? Either the program can crash, it can abort, it can overflow, it can run forever into infinite loop, and anything else can happen to the program. And that is why the whole subject revolves around this question, is my program P correct? Or are the program properties satisfied? When I talk about that, we will constantly look into program P must always do the task that it is designed for. Whenever you are writing programs in HackerRank or some sort of lead code problems you're solving, after you write a program, you go through the submission and you have some test cases. These test cases will then test, right? Now, are these test cases verifying the program? Yes. Why? Because they have certain sort of inputs, and with those inputs, you are expecting certain sort of outputs. When a program P prepared for making a particular task or fulfilling a particular task, it will direct from input to the expected output. And to get to the expected output, you have to give a specific input. You cannot give anything but a specific input. We will be discussing this a lot because this is of prime importance to understand. The idea behind the whole logic is to know that the inputs that you provide gives you certain sort of outputs. And this is the core of the deductive verification. Now what we want from the programs is to specify the functional requirement or meet the functional specifications. Now what do specifications meet? We will be discussing this as we move below. Now, as I said, there are two types of techniques. One is model checking, other is deductive verification. When I talk about model checking, I am talking about models that look like this or can be of different forms. We will be doing it in the second part of the course, not the second part of the module, second part of the course. Now, when we talk about deductive verification, we are talking about Hoare logic. What are we talking about? Hoare logic. And this is very important to understand because it will help us prove that a program, because we are only feeding program to deductive verification, it will help us prove that our program is correct. And when I talk about correctness, it has to be meeting certain safety properties, liveliness properties, and functional properties. If you don't know about them, I will again ask you to go back to the slide, the first lecture that we discussed, and there you will get a gist of what it is. But later, as we move on, we'll dive deeper into it. Now, my question to you would be, why do we call it deductive verification? And why do we use it? What is the need of using it? When I'm talking about deductive verification, the name says it all. It is a verification technique that is based on inference rules. Now, inference rules means something that you can infer from. Okay? Infer from. This is important. So, something that you can infer from. You're given something and seeing that you can make sure that, okay, this particular concept is linked to this concept, right? So verification conditions are based on inference rules, giving proofs from what we infer. That is why it is named as deductive verification. So while doing a program, we will be doing some sort of verification that will help us infer. After that method, the method that we follow, we'll be able to infer that this program is either correct or not correct. Both. So whatever happens, we will be able to filter out that. Now, second, why do we use it? We use it because it will directly operate on the program, that is the source code. If it doesn't operate on the source code, then there can be only other technique, which is model checking. And model checking is very important. But right now, because we are focusing on the program and we do not have to convert it into a model, it is the convenient technique that we can use. Second reason is it will provide clear math. So we will go through the grammar, we'll go through the rules that are followed while doing Hoare calculus or while proving a program correct with deductive verification. Now, CBMC is another tool that is used in model checking. Now, this is not applicable for infinite state space. Places where there are infinite state spaces, CBMC or bounded model check is not good. And here we can use deductive verification to support the unbounded loops as well. Why and how? With the help of loops, we find something that is really common, and this is something which is of prime importance in this whole lecture or even in the whole series of deductive verification. Now, what will be the workflow? The workflow will go as, whenever you're making a program, suppose you're making a program for your business idea where you want to build up a website that is helping other students know about the nitty-gritties of applying for a university. Now, these are the informal requirements. You write the formal requirements in natural language, saying this is something that I want, this is something that I want, and you will list all the listings of that particular idea for which you want to create a software. Now, while you're devising this software, you also need to verify. Once you've verified, you can say, yes, my software works fine and it can help you do the task as per the requirement, because we want to meet the expectation, that is the output expectation. Now, informal requirements once given, specifications or formulations can be made of the informal requirements. The informal requirements, let us suppose there's a program for finding positive and negative numbers. Now, you can say that x can be greater than 0 or x can be less than 0, but not 0 anywhere. That is, you're giving your input, you're ranging your input between these two so as to get either a positive or a negative number. We are not considering 0, suppose, for a particular program. Now we will be formatting. This is x is greater than 0, x is less than 0, and we put an and. What is this? This is a formulation. This is a specification. Now this specification, when we design and implement the software, we provide a specification, a formula that is also later known to be part of Hoare triple. So what we do, you remember this, we give this specification to the software and verify if this input generates the output that we want it to generate. Am I making sense? If you have any questions, please comment below and let us know that what your questions are. We'll try to address them. Secondly, as we move forward, we will give you some time to do some questions. So do not panic. Right now, understanding the concept is very important, and I hope you will be doing it really nicely. This is the foundational level that we are building upon. After this, the concepts will go really fast, and for them to make sense, you need to understand and listen very carefully what we are teaching right now. Okay, so we move forward. For a program P, there's a program. Let's say we name a program P. You can name anything. You can, if you're making a program for copying something, you can write a program as copy. Or you are making it as a sum of two numbers, you can write sum, multiplication, or Gaussian sum, or whatsoever you want, you can name the program. For simplicity, I'm naming the program P. Now, for any program P, we define Hoare triples. Hoare triples are the logical formulas or formal specification. As I showed you just now, that we can make use of formulas to make these properties, these formal specifications. Now, Hoare triple, what will it do? What is it? I will tell you. But what will it do? It will prove that the program is correct. And in order to prove the program is correct, we need to make what? We need to make formal specification or logical formulas. So we check those formulas throughout the program. Moving further, there's another term which I would like to highlight. If you see it in any book or somewhere specifically, it's known as caveats. It's a warning of specific stipulation, condition, or limitation. Sometimes your program also gives some warnings. Similarly, this is the warning. For our case, this warning is for the type of Hoare triple we are building. Right? So we want to investigate the gaps between the natural language and the formulations. And what does the caveats do? Caveats highlights the warning. It highlights specific limitation that the system holds while converting natural language to the formulation. Now, as we move forward, we need to understand what Hoare triples are. In order to understand what Hoare triples are, we need to understand simple things that it holds. Okay, so if we're talking about Hoare triple, it works on core language. It is also called while language. Now, we will have our programs will have these three things. In every program, you will find these three things. This E is called as expression. B is called as Boolean. And C is called as command. Now, these three things will make our code or program. And these programs will then be fed with the property to a model to understand what this program is supposed to do and what it is doing. When we've already broken down this, let's talk about E. E is the expression. It can be a constant, it can be a variable, it can be negative, it can be positive, it can be multiplication. Basically, this is addition, this is Again, another sort of expression that you can express. Now when we talk about B means Boolean. Okay. Now Boolean, this is used for conditions if you see. This one is basically for variables and assignments. Even when you're using a part called composition of statements, you can use this. B is used for conditions specifically. All the conditions. So it can be true, it can be false, it can be not B, it can be B and B. So when you're writing, if you know C program or any other program, you write if condition. And this condition can be written in one of these forms. This is what we are highlighting here. And finally comes the commands. The commands can be assignment, can be composition, can be if else, if it can be while B, C. Now what does Hoare triples do? For a program P, Hoare triple will capture P's requirements. Whatever you want the program P to do, it will capture those requirements as logical formulas or formal specification. Now when you convert them into formal specification or logical formulas, you can make your precondition, right? So you check your precondition with respect to the post condition, which you usually do it backwards, because in order to understand what exactly the Hoare triple does, it will go backwards and we will discuss it in detail later. Now, understanding what Hoare triple is obviously it's a triple, so there are three values that we will be giving. P you already know is a program, okay? And phi is a precondition. What does a precondition mean? Before a program is executed or run, we will be giving a condition for which the program should hold true. If this program holds true and when it terminates, it gets into a state called psi, this psi should also hold in all the states where phi holds. Okay, so these three are linked, and you can take an example of HackerRank code. Suppose you've written a positive negative 0 code, and now they're asking you to pass it through test cases. The test cases are certain types of inputs that are assumed by the model, and then it gives a certain type of output if your program is correct. If it is not correct, then it will not give and you need to reiterate it. But for now, let us assume that program is correct and you get phi as well. Now the specification, this complete specification is called as Hoare triple. We read it as if P runs in a state where phi holds, and if P terminates, then psi holds in the state with which P terminates. This is very important. And if phi, which is the precondition that doesn't hold in the program can return anything, and that is called as garbage in, garbage out, which we will study. Now I would like to talk about the very important concept which is known as states of program.